Okay, let's recall what we were doing last time. So we had started looking at scattering in interacting theories, and we defined in and out states, which are states defined at, or basis states defined at time t equal to 0. Okay, so let me quickly remind you what we were doing. So we had defined in states and out states. Okay. So let me write it as, so in general, in any theory I'm writing, I'm not necessarily in a real scalar field theory, but any arbitrary theory. So I will write alpha out. Okay, so that specifies some out state where alpha are the appropriate labels, and similarly we will write beta in. Okay, so these are in and out states. So for example, here beta will specify the particle content for t going to minus infinity. So if you take this in state and you evolve it by folding it appropriately with folding functions, and you evolve backward in time, and in the far past you are going to see it as free particles which are well separated. Okay, and the particle content is described by beta. Okay, and similarly in far future this out state will evolve into a set of particles which will be labeled by this alpha. And in case of real scalar field theory, it's only the momentum which is the label, and the total number of particles in the state, that would be the label. Okay, so that is what it is. And then maybe let me just be more specific for the real field theory case. So this, as I wrote last time, it will be these labels. Okay, for real scalar field theory. And alpha out, Pn out. Okay. And we also define S matrix element to be the following. S alpha beta was defined to be an inner product of these two states. So if for state beta, this, so the amplitude of state beta in to be found in alpha out. Okay, that is what the definition of S matrix is. And for the case of real scalar field theory, this would be this thing I wrote as S. So here let's see beta. So anyway, these labels are not matching. So in is, no, that's fine. So in is Q1 is labeled by these labels, and out is labeled by these momenta. Okay, so that's how we wrote S alpha beta in this case. And then this was just this inner product. P1 to Pn out, that's correct. Okay, that's what we had written last time. Okay, so we'll make some elementary observations this time, and more detailed studies will be done next time. So let's ask first thing, what's the inner product of these states alpha out and beta in? within themselves, not of an out state within state. So let's say I am given a state alpha out and another state alpha prime out, okay, where alpha is not equal to alpha prime. Okay. For example, if let's say both alpha and alpha prime, let's say they both contain 5 particles, 5 labels, P1 up to Pn and Q1 up to Qn, then alpha not equal to alpha prime would mean that these 5 labels are not the same as those other 5 labels. Okay, that is what it means. So we would like to know what is this. So it's easy to understand what this is. So suppose you take a basis state at time t equal to 0, let's say it is alpha out, and evolve it into far future. So it will correspond to a set of particles which are labeled, which are the particle content will be alpha. Okay. If you start with a different state alpha prime out, then in far future the particle content will be alpha prime. Okay. Now since we are saying alpha and alpha prime are not the same, they are different, then these two states in far future are different, and there is no possibility of a state alpha out to evolve into, to give a state in far future that corresponds to the state that you would have got by evolving alpha prime out. Okay, so that since the possibility is 0, that amplitude is 0, so we can write here that's 0. Okay, now we can ask about the normalization of these states. So what is in general, where I am allowing now alpha prime to be equal to alpha also. Okay, so remember these basis states alpha out, they evolve to these states which correspond to free particles, and we have already talked about these free particles in the previous course, and you know how these states are normalized. You normalize them to Dirac delta function. Okay, so the same will be true here. You can almost see that this is going to be proportional to this is just a notation, shorthand notation, but this will be proportional to this. Okay, where in the case of where alpha is only the momentum labels, you will have Dirac delta functions, delta cubes. But let me use a shorthand notation and just write delta of alpha minus alpha prime. Okay, so clearly when alpha is not equal to alpha prime, then you get 0, so they are orthogonal. And when they are equal, you get, they are normalized to delta functions. So, and in fact, instead of writing delta like this, I will pretend as if these labels are discrete. Okay, that's just, I'm going to pretend it, but you understand that these are involving both delta functions and maybe Dirac delta, Kronecker delta functions. So I'm just writing it like this. But if you don't like this, you can think of it in these terms. Anyhow, so now that I have written down the normalization for the out states based on some intuition and some hand waving, we'll make it more precise later, and I'll convince you that indeed what I'm saying is true, unless it already appears obvious. I can now also similarly write down for in states. Okay, and remember when you are looking at the inside in the far future, you have many possibilities. It's not just two particles you collide, you can collide n number of particles. So all those possibilities are there, and that is why you have lots of possibilities for the in state also. Okay, Good. So we have these things, and then I had also remarked that the these states form a complete set. Okay, meaning any state in the final state can be expressed as a linear sum of or a superposition of the out states. Similarly for the in states. So this implies that I should have a completeness relation. And that would be alpha I'm using for out, where I sum over alpha. So again, alpha is not only discrete, it would be continuous also, but I'm just using sigma, and it is understood that if those indices which are continuous, you have to integrate over, not sum over. Okay, and this will be that will be identity. And similarly for your in states. Okay, so this is the completeness relation. Okay. Also, remember these are two different bases for the same Hilbert space. Okay, it's not that they are living in two different Hilbert spaces, these in and out states. And clearly you can express out states, for example, in terms of in states and vice versa. So let me do that. Let me also write this as, since the in states since the in states and out states are two different bases of the same Hilbert space, I can do the following. So I take, let's say, beta in, which I can write it as identity times beta in, and for the identity I insert this completeness relation. So I get alpha out, again here alpha out, sum over all alpha, and here you have a beta in. And what is this? This is just S alpha beta, that's the S matrix element. Okay, so I've written beta in, one of the basis elements, as a linear sum of the out states, and the coefficients are precisely the S matrix elements. Okay, so you understand what we are doing. Okay, we want to know these coefficients S alpha beta. Okay, once you know these elements, you will be able to predict what will happen in the future. Okay, so these coefficients are the S matrix elements. Okay, good. Now I'll show you something else. So, you are going from, when you are going from in state to out state, what you are doing is you are changing bases. You are going from one basis to another basis in the Hilbert space. Okay, and these bases, as I have argued here, these are orthonormal bases. Okay, so you are basically going from one set of orthonormal bases to another set of orthonormal basis vectors. Okay, so if you do so, then your transformation matrix, okay, will have some property. It will be unitary, and that's what I'm going to show, that your S matrix is unitary. So let's show this. So I take some state gamma in and take its product with another, no, not did I call it sigma? No, let's call it delta n. Okay, let's evaluate this. Now what is this object? This object is just delta of delta gamma, okay, where remember this Kronecker delta is a would involve in general Dirac delta functions also, because delta is not only discrete, it also has continuous parameters like momenta. So this is this object, but I can write this thing by inserting a complete set involving out states. So this would give me, so here I insert a set of out states, and okay, which is equal to this I can take in. So you have delta in alpha out, and you have here out gamma in, which I will write as this. I can write as alpha out delta in, but then I have complex conjugation alpha out gamma in, and this is what this we have been calling S matrix, okay, S alpha gamma. So you write this as S alpha gamma, and this is what S alpha delta star, okay, and that is the condition of unitarity, that this sum is equal to, let me write this thing here, delta of delta gamma. I wish I had chosen instead of delta something else here, but anyway, so this is the condition of unitarity. So we say that the S matrix is unitary. Okay, so I know something about the S matrix. It's unitary. Now let's try to have a little bit more understanding, actually very little understanding of the in and out states. Okay, we are going to spend some time on it, but there's something very trivial that I can already say about it. So imagine you have one particle state. Okay, so you have only one particle. So far in past you have one particle. Now since there is only one particle and there is nothing else interacting with it, that one particle is going to evolve into one particle state in future also. So it's one particle state remains one particle state. So when you take that one particle state, okay, you can decompose into its into various momentum components. Okay, so the basis states at time t equal to 0, let's focus on the in states, you will label them as k in. Okay, and when you look at far future and you go backwards at time t equal to 0, you will have basis states as p out. Okay, and since a single particle state evolves to single particle state, there is nothing else going to happen. It's clear that a basis state k in is same as k out. So there is no distinction between in and out state as far as single particle states are concerned. See, there is only one label k. It's not k comma p, it's 1. Okay, so even though the theory is interacting, your single particle states, your in states corresponding to single particle states and in state out states corresponding to single particle state, they are the same. There is no distinction between them. And also you can imagine the vacuum. Okay, so a vacuum will evolve into vacuum. A vacuum will not turn into n particle states. Okay, because that will violate all these conservation laws. So vacuum is going to remain vacuum. So it's again clear that vacuum n is same as vacuum out. Okay, so these are few things that I wanted to say in this video, and we would start a more careful analysis of these things, and some of the things which I have written based on intuition or some hand waving, I will make them more concrete next time. Okay, so see you in the next video.